This is an audio recording for visually impaired students from the book Pradeep's Physical Chemistry, Volume 1 by Dr. S.C. Khetrapal. Electrochemistry Part 1 Electrolytic Conduction and Transport Number. Heading 2.1 Electrolytic and Metallic Conduction and Factors Affecting Them. Heading 2.1.1 Electrolytic and Metallic Conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes. First, those which conduct electricity without undergoing any decomposition. These are called electronic conductors. Example, metals, graphite, and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Second, those which undergo decomposition when current is passed through their aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example, solution of acids, bases, and salts in water, fused salts, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acids, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc. and most of the inorganic salts. These dissociate almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acids, example CH3COOH, HCN, H2CO3, H3PO4, etc. and weak bases, example NH4OH, CaOH whole twice, AlOH whole thrice, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solutions of which do not conduct electricity are known as non-electrolytes. Next heading 2.1.2 Factors affecting electrolytic conduction. The conductance of the solution of an electrolyte depends upon the following factors. First, interionic attraction, which depend upon the interaction between the ions of the solute and hence are called solute-solute interactions. On this basis, the substances are classified as strong electrolytes and weak electrolytes, as already mentioned. Second, solvation of ions, which depends upon the interaction between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interactions. Then 10% ionized in the aqueous solution. However, there are many electrolytes whose behavior is intermediate between strong and weak electrolytes. That is, their dissociation is less than 100% but greater than 10%, and similarly their conductance is less than that of strong electrolytes but greater than that of weak electrolytes. Such electrolytes are called moderate or intermediate electrolytes. Example, orthochlorobenzoic acid, orthonitrobenzoic acid, and cyanoacetic acid. Third, viscosity of the solvent, which depends upon the solvent-solvent interactions. The effect of all these factors decrease the increase of temperature. Hence, the electrolytic conduction increases the increase of temperature. On the other hand, the electrical conduction of the electronic conductors decreases with increase of temperature. Alternatively, the factors on which electrolytic conduction depends are as follows. First, nature of electrolyte. Strong electrolytes ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also to a small extent. Second, nature of the solvent. Electrolytes ionize more in a polar solvent and hence greater is the polarity of the solvent, greater is the ionization and hence greater is the conduction. Third, concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte, the ionization is less, whereas in a strong electrolyte, the interionic attraction are high at higher concentrations. With dilution, Interionic attraction decrease and hence conduction increase. Fourth, temperature. On increasing the temperature, the dissociation increases and hence the conduction increases. Next heading 2.1.3. Difference between metallic conductors and electrolytic conductors. The main points of differences between metallic conductors and electrolytic conductors may be summed up in table 2.1. Table 2.1. Difference between metallic conductors and electrolytic conductors. Metallic conductors. First, flow of electricity takes place without the decomposition of the substances. Electrolytic conductors. Flow of electricity takes place accompanied by the decomposition of the substance electrolyte. Second, metallic conductors. Flow of electricity is due to the flow of electrons only. That is, there is no flow of matter. The conductance depends upon the structure and the density of the metal and the number of valence electrons per atom. Electrolytic conductors. Flow of electricity is due to the movement of ions and hence there is flow of matter. Third, metallic conductors. The electrical conduction decreases with increase of temperature. This is because kernels start vibrating which produce hindrance in the flow of electrons. Electrolytic conductors. The electrical conduction increases with increase of temperature. This is generally due to increase in dissociation or decrease in the interionic attraction. Fourth, metallic conductors. The resistance offered by metal is also due to vibrating kernels. Electrolytic conductors. The resistance shown by an electrolyte solution is due to factors like interionic attractions, viscosity of solvent, etc. Next heading 2.2. Electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small or large extent. The law that gives the exact value of the resistance is known as Ohm's law. It states that if to the ends of a conductor a voltage E is applied and a current I flows through it, then the resistance R of the conductor is E upon I. In addition to metals, graphite and certain minerals also conduct electricity due to presence of free electrons in them. Hence, they are collectively called as electronic conductors. Current is generally measured in ampere, whereas voltage is measured in volt. If 1 ampere current flows through a conductor when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm, written as 1 ohm. Thus, according to Ohm's law, R is equal to E upon I, or ohms is equal to volts upon amperes. In terms of SI base units, ohm is equal to kg meter square per second cube area cube. This is explained below. Ohm is equal to V upon A, work per unit charge upon A, is equal to work upon charge into 1 upon A, which is equal to F into L upon A into S into 1 upon A. It is seen then, like metallic conductors, solution of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will allow less electricity to flow through it. This result also follows from Ohm's law, according to which I is inversely proportional to 1 upon R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. Thus, C is equal to 1 upon R. It is a common practice to speak of the conductance of a solution rather than its resistance. Units. The units of conductance are Simon or reciprocal ohms, written as ohm inverse or mho mho, or R. 1 Simon is equal to 1 ohm inverse. For example, if a solution has a resistance of 10 ohms, it is said to have a conductance of 1 upon 10 ohm inverse, or 1 upon 10 mhos, or 1 upon 10 ohm inverse, or 1 upon 10 Simons. Next heading 2.3. Specific, equivalent and molar conductivities, conductances and relation among them. Heading 2.3.1. Specific conductance or specific conductivity, or simply called conductivity. It is observed that resistance R of a conductor is first directly proportional to the length L of the conductor, and second inversely proportional to its area of cross section A. That is, R is proportional to L upon A, or R is equal to rho L upon A, where rho is a constant of proportionality called specific resistance or resistivity. Its value depends upon the material of the conductor. The reciprocal of resistivity is known as specific conductivity or simply conductivity. It is denoted by kappa or K. Thus, if K is the specific conductivity and C is the conductance of the solution, then R is equal to 1 upon C and rho is equal to 1 upon K. Kappa is the most commonly used symbol for specific conductance. However, symbol K has been used in the book for simplicity. 1 upon C is equal to 1 upon K into L upon A. K is equal to C into L upon A. Now, if L is equal to 1 centimeter and A is equal to 1 square centimeter, then K is equal to C. Hence, specific conductance or specific conductivity, or simply called conductivity, of a solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of 1 centimeter cube of the solution of the electrolyte, or in terms of SI base units, it is defined as the conductance of 1 meter cube of the conductor. If the volume of the solution is V centimeter cube, the specific conductance of such a solution is at this dilution V is written as Kv. Similarly, at concentration C, it is represented as Kc. Units: resistivity rho is equal to Ra upon L. Ohm centimeter square upon centimeter is equal to ohm centimeter or ohm meter in SI units. 1 ohm meter is equal to 100 ohm centimeter. Specific conductance K is equal to 1 upon rho is equal to 1 upon ohm centimeter is equal to ohm inverse centimeter inverse, or ohm inverse centimeter inverse, or Simon centimeter inverse, or Simon meter inverse in terms of SI units. 1 Simon centimeter inverse is equal to 100 Simon meter inverse. Next heading 2.3.2, equivalent conductance or equivalent conductivity. For comparing the conductance of the solution of different electrolytes, it is essential that first, the volumes of the solution should be same, and second, they must contain such definite amount of the electrolytes which give ions carrying the same total charge. The best choice is therefore to consider the solution having equal volumes and containing their corresponding gram equivalent masses. The conductance of such a solution is called its equivalent conductance. Hence, equivalent conductance of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and the area of the electrodes is so large that whole of the solution is contained between them. It is represented by lambda equivalent. Relationship between equivalent conductance and specific conductance. The equivalent conductance of a solution is usually not found directly but is calculated from the specific conductance. The relationship between equivalent conductance and specific conductance may be obtained as follows. Consider a rectangular vessel with its two opposite walls 1 centimeter apart and made of some metal sheets so that these act as the electrodes. Case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of this solution will be then its specific conductance. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent conductance by definition. Thus, when 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is considered, the equivalent conductance is equal to its specific conductance. Case 2. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken. The conductance of the solution will be still equal to its equivalent conductance at this dilution, but now there will be 4 cubes, each of volume 1 centimeter cube as shown in figure 2.2. The conductance of each 1 centimeter cube of the solution is equal to its specific conductance, so that the total conductance of the solution, that is equivalent conductance, is 4 times the specific conductance. In general, if the volume of the solution containing 1 gram equivalent of the electrolyte is V centimeter cube, we have equivalent conductance is equal to specific conductance into V. So lambda equivalent is equal to kV into V. In terms of concentration, if the solution has a concentration of C gram equivalent per liter, that is gram equivalents are present in 1000 centimeter cube of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 upon C. Hence the above expression may be written as lambda equivalent is equal to Kc into 1000 upon C equivalent is equal to Kc into 1000 upon normality. Note carefully that in the above expression, V is the volume of the solution in centimeter cube containing 1 gram equivalent of the electrolyte, and C is the concentration in gram equivalent per liter. Units: lambda equivalent is equal to K into V, that is ohms inverse centimeter inverse into centimeter cube upon gram equivalent, is equal to ohm inverse centimeter square or gram equivalent inverse, or ohm inverse centimeter square equivalent inverse, or Simon centimeter square equivalent inverse, or Simon meter square equivalent inverse in SI unit. 1 Simon meter square equivalent inverse is equal to 10 raised to power 4 Simon centimeter square equivalent inverse. Next, heading 2.3.3, molar conductance or molar conductivity. The molar conductance of a solution is defined in a manner similar to that of the equivalent conductance as under: the molar conductance of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of the electrode is so large that the whole of the solution is contained between them. It is usually represented by lambda m, relationship between molar conductance and specific conductance. As in the case of equivalent conductance, the molar conductance is related to the specific conductance as follows: lambda m is equal to Kv into V, or lambda m is equal to Kc into 1000 upon C is equal to Kc into 1000 upon molarity, where K is the specific conductance and V is the volume of the solution containing 1 mole of the electrolyte, and C is the molar concentration, that is mole per liter or mole per decimeter per cube. Units: comparing with the equivalent conductance, the units of lambda m will be ohm inverse centimeter square mole inverse, or Simon centimeter square mole inverse, or ohm inverse centimeter square mole inverse, or Simon meter square mole inverse in SI unit. 1 Simon meter square mole inverse is equal to 10 raised to power 4 Simon centimeter square mole inverse, or 1 Simon centimeter square mole inverse is equal to 10 raised to power minus 4 Simon meter square mole inverse. Next, heading 2.4, measurement of electrolytic conductance, specific conductance, equivalent conductance and molar conductance. First, electrolytic conductance. Conductance is the reciprocal of resistance. Hence, the conductance can be obtained by the measurement of the resistance, and the latter can be found by the principle of Wheatstone bridge method shown in figure 2.3. It consists of 4 arms containing the resistances R1, R2, R3 and R4. R1 is the variable resistance and R2 is the unknown resistance. When null point is obtained, that is, there is no deflection in the galvanometer G, R1 upon R2 is equal to R3 upon R4. Knowing the values of R1, R3 and R4, R2 can be calculated. In finding the resistance of the solution of an electrolyte, a special type of cell has to be used such that the solution is present between the 2 electrodes. The cell thus used is called conductance cell. It is made up of Pyrex glass and has 2 platinum electrodes at a fixed distance apart, shown on right hand side of figure 2.4. The most serious problem in the measurement of the resistance and hence the conductance of the solution of an electrolyte is that if direct current is used, it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes change, and this results in the change in the resistance of the solution. These effects are called polarization effects. To overcome this problem, an alternating current in the audio frequency range of 550 to 5000 cycles per second is used. However, when the alternating current is used, ordinary galvanometer fails to detect the null point, hence the galvanometer is replaced by earphone. Further, to minimize the polarization effect, the electrodes are coated with platinum black, that is finely divided platinum deposited on the electrodes electrolytically. To sum up, the three modifications required in the usual Wheatstone bridge method are: first, source of direct current is replaced by a source of alternating current, which is either an induction coil or a vacuum tube oscillator, which is quieter and gives more symmetrical current. Second, galvanometer is replaced by an earphone. Third, electrodes of the cell are coated freshly with platinum black before use. The complete assembly for the measurement of the electrolyte conductance is shown in figure 2.4. A suitable value of the resistance R is introduced from the standard resistance box such that when the sliding contact, that is the jockey J, is moved along the stretched wire, the sound in the earphone is reduced to the minimum at a point somewhere in the middle of the wire AC, say at the point D. Then if X is the resistance of the electrolytic solution by Wheatstone bridge principle, resistance R upon resistance X is equal to resistance of wire AD upon resistance of wire CD is equal to length of AD upon length CD. Resistance X is equal to resistance R into length CD upon length AD. Thus, knowing the resistance R and the balance point D, the resistance X of the electrolytic solution can be calculated. Then conductance C is equal to 1 upon X is equal to 1 upon R into length AD upon length CD. Second, specific conductance. Specific conductance, or simply called conductivity K, is related to the conductance C according to the expression K is equal to C into L upon A. Thus, the specific conductance of a solution can be determined by measuring its conductance and the distance L between the electrodes and the area of cross-section A of each of the electrodes. But it is not convenient to measure L and A accurately. However, for a particular cell, L upon A is constant, and this constant is called cell constant. That is, L upon A is equal to cell constant. So, specific conductance kappa is equal to conductance C into cell constant K cell. Thus, the cell constant of any particular cell can be found by measuring the conductance of a solution whose specific conductance is known. For this purpose, generally specific conductance of KCl solution are used, which are known accurately at different concentrations and temperatures. For a few concentration at a temperature of 298 Kelvin, these values are given below. Concentration of KCl solution: 1.000 m. Conductivity or specific conductance: 0.113 Simon centimeter inverse. Concentration of KCl solution: 0.100 m. Conductivity: 0.0129 Simon meter inverse. Concentration of KCl solution: 0.010 m. Conductivity: 0.00141 Simon centimeter inverse. Knowing the value of the cell constant, the specific conductance of the given solution can be determined by measuring its conductance and multiplying the value with the cell constant. Third, equivalent conductance. Equivalent conductance, lambda equivalent, is related to the specific conductance K according to the equation lambda equivalent is equal to K into 1000 upon C equivalent is equal to K into 1000 upon normality, where C equivalent is the concentration of the solution in gram equivalent per liter, that is the normality of the solution. Thus, knowing the normality of the solution and the specific conductance K, lambda equivalent can be calculated. Fourth, molar conductance. The molar conductance is related to the specific conductance according to the relation lambda m is equal to K into 1000 upon Cm is equal to K into 1000 upon molarity, where Cm is the molar concentration. Thus, knowing the molar concentration C and the specific conductance K, lambda m can be calculated. Conductivity water. For accurate results, the solution should be prepared in a specific purified water whose own conductance is very small. Such water is called conductivity water. It is obtained by distilling good distilled water to which a liter potassium permanganate has been added. Water of this type has a specific conductivity of about 8 into 10 raised to power minus 7 ohm inverse centimeter inverse. Alternatively, to get the resistance of the electrolyte, the resistance of water used for making the solution may be determined and then subtracted from the resistance of the solution. Next heading 2.5, variation of conductance, specific conductance, equivalent conductance and molar conductance with dilution. In general, electrolytic conductance as well as the equivalent conductance and molar conductance increase with dilution, whereas the specific conductance of an electrolytic solution decreases with dilution. The reasons for such a behavior are briefly explained below. The conductance of a solution is due to the presence of ions in the solution. The greater the number of ions, the greater is the conductance. As on dilution more ions are produced in solution, so the conductance should also increase on dilution. The specific conductance of an electrolyte falls with dilution because the total number of current carrying particles, that is ions, increases with dilution, but ions present per centimeter cube of the solution becomes less and less on dilution. However, the increase of equivalent and molar conductance on dilution is due to the fact that these are the products of specific conductance and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte. As the decreasing value of specific conductance is more than compensated by the increasing value of V, so the values of lambda equivalent and lambda m increase with dilution. Next heading 2.6, variation of molar conductance with concentration for strong and weak electrolytes. As already mentioned in the beginning of this chapter, there are two types of electrolytes, namely strong electrolytes and weak electrolytes. The variation of molar conductance with concentration or dilution for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes. As discussed later in more details in section 2.7, the molar conductance of strong electrolytes is found to vary with concentration according to the equation lambda mc is equal to lambda m naught minus b root c, where b is the constant depending upon the type of the electrolyte, the nature of the solvent and the temperature, and lambda m naught is the molar conductance at infinite dilution called limiting molar conductance. This equation is called Debye-Huckel-Onsager equation and is found to hold good at low concentration. Thus, if lambda mc is plotted against root c, a linear graph is obtained for low concentrations, but it is not linear for higher concentrations as shown in figure 2.5, in which KCl has been taken as an example of a strong electrolyte. Further, the curve obtained for a strong electrolyte shows that there is a small increase in conductance with dilution. This is because the strong electrolyte is completely dissociated in solution and so the number of ions remains constant. At higher concentration, the greater interionic attractions retard the motion of ions and therefore the conductance falls with increasing concentrations. With decrease in concentration, that is, with dilution, the ions are far apart and therefore the interionic attractions decrease, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution designated as lambda m naught or lambda m infinity. Conductance behavior of weak electrolytes. As a weak electrolyte dissociates to a much lesser extent as compared to a strong electrolyte, therefore the conductance of a weak electrolyte is much lower than that of strong electrolyte at the same concentration. This is shown in figure 2.5, in which acetic acid has been taken as an example of a weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because as the concentration of the weak electrolyte is reduced, more of its ionizes, thus increasing in conductance with decrease in concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. NaCl, BaCl2, MgSO4 are called 1,1, 2,1 and 2,2 electrolytes depending upon the charges on cations and anion for a given solvent and temperature. All electrolytes of a particular type have the same value for the constant B. Next heading 2.7, Arrhenius theory of ionization. Heading 2.7.1 Postulates of Arrhenius theory. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolytes towards colligative properties, that is, higher values of osmotic pressure, elevation in boiling point, depression in freezing point, and lowering of vapor pressure than expected, Arrhenius in 1887 put forward a theory about the electrolytes. This theory is known as Arrhenius theory of electrolytic dissociation. The main points of this theory in a modified form are summarized below. First, an electrolyte when dissolved in water splits or dissociates into positively and negatively charged particles called ions. The process is called ionization, or more correctly electrolytic dissociation. Example, NaCl gives Na positive plus Cl negative. Second, the total charge carried by the positive ions is equal to the carried by the negative ions, so that the solution as a whole is electrically neutral. Third, on electrolysis, the positive ions migrate towards cathode and hence are called cations, while the negative ions migrate towards anode and therefore called anions. Fourth, the ions formed constantly reunite to form the undissociated molecules till ultimately there is an equilibrium between the ions and the undissociated molecules. Example, NaCl gives out N positive plus Cl negative. In other words, the whole of the electrolyte may not dissociate into ions, instead only a part of the electrolyte may dissociate into ions. The fraction of the total number of molecules of the electrolyte that dissociates into ions is called the degree of ionization or dissociation. It is usually denoted by alpha, that is, degree of dissociation is equal to number of molecules dissociated upon total number of molecules taken. Fifth, the degree of dissociation increases with dilution and becomes maximum at the infinite dilution. Sixth, the conductance of an electrolytic solution is due to the ions produced by the dissociation of the electrolyte. Greater the dissociation, the higher is the conductance. Substances like mineral acids, alkalis, and most of the salts which show a high conductance is due to the fact that they possess high degree of dissociation, that is, their molecules are almost completely dissociated into ions. In the aqueous solution, such substances are called strong electrolytes. On the other hand, the substances like organic acids and bases and some of the inorganic acids like H2CO3, H3PO4, etc., and inorganic bases like NH4OH, CaOH whole twice, etc., which show poor conductance is due to the fact that they possess low degree of dissociation, that is, they are only partially dissociated in the aqueous solution. Such substances are called weak electrolytes. Seventh, the ions produced by the dissociation of an electrolyte behave like molecules towards colligative properties. For example, with NaCl molecule dissociates to give two ions via Na positive and Cl negative. Hence, the observed value of any colligative property is double than the expected value. Eighth, the properties of an electrolyte are the properties of its ions. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the properties of a base are due to the OH negative ions produced in the aqueous solution. Next heading 2.7.2 Evidence in favor of Arrhenius theory. The direct evidence for the Arrhenius theory came from the X-ray studies which showed that solid substances which behaved as strong electrolytes existed in the ionic form and not in the molecular form. Example, NaCl is found to exist as Na positive, Cl negative. Further, Arrhenius theory is able to explain a number of facts and phenomena related to electrolytes which lend support to the theory. A few of these phenomena are briefly explained below. First, electrolytic conductance. It has been explained in postulate 6 of the Arrhenius theory that the conductance of the solution of an electrolyte is due to the presence of the ions produced by the electrolyte on dissociation. Strong electrolytes possess high degree of dissociation and hence show greater conductance, whereas weak electrolytes dissociate to a small extent and hence show low conductance. Second, variation of conductance with dilution. It is observed that the specific conductance decreases, whereas conductance as well as equivalent conductance increases with dilution. The explanation is evidently based on postulate 5th and 6th of the Arrhenius theory. The equivalent conductance and the dissociation of the electrolyte vary in such a similar manner with dilution that the degree of dissociation of an electrolyte at any concentration can be expressed in terms of equivalent conductances as follows: alpha is equal to lambda c upon lambda naught, where lambda c is the equivalent conductance at the given concentration and lambda naught is the equivalent conductance at infinite dilution. Third, electrolysis. According to postulate first of the Arrhenius theory, an electrolyte when dissolved in water dissociates into ions. Thus, the function of the electricity is only to direct the ions towards the electrodes. Fourth, colligative properties. The reasons for the anomalous results observed about the colligative properties for the solution of an electrolyte has already been given in postulate 6 of the Arrhenius theory. The quantitative explanation of the anomalous results about colligative properties of strong electrolytes was given by Van 't Hoff. He introduced a factor I called Van 't Hoff factor, defined by the expression I is equal to observed value of the colligative property upon normal value of the colligative property. The factor I could be determined experimentally by dividing the observed value of a colligative property, that is, osmotic pressure, lowering of vapor pressure, elevation in boiling point, or depression in freezing point, with that of the solution of a normal substance like sucrose having the same molar concentration. The Van 't Hoff factor I could be used to find the degree of dissociation as follows. First, for electrolytes of the type AB, example NaCl, KCl, etc., suppose we start with 1 mole of the electrolyte and alpha is the degree of dissociation. Then we have AB gives out A positive plus B negative, number of moles before dissociation 1, number of moles after dissociation 1 minus alpha, and for A and B alpha alpha. Therefore, total number of moles after dissociation is equal to 1 minus alpha plus alpha is equal to 1 plus alpha. Assuming normal behavior, that is, if there were no dissociation, number of moles would have been 1, directly proportional. Since the value of a colligative property is proportional to the number of particles, which in turn is directly proportional to the number of moles, Van 't Hoff factor I would be given by I is equal to 1 plus alpha upon 1, so that alpha is equal to I minus 1. Second, for electrolytes of the type AB2, example BaCl2, MgCl2, etc., starting with 1 mole of the electrolyte and assuming that alpha is the degree of dissociation, we have as before initial number of moles 1, number of moles after dissociation 1 minus alpha. Therefore, total number of moles after dissociation is equal to 1 minus alpha plus 2 alpha, as here it was A 2 positive plus 2B negative. So 1 minus alpha plus 2 alpha is equal to 1 plus 2 alpha. Hence, as in the earlier case, I is equal to 1 plus 2 alpha upon 1, or 2 alpha is equal to I minus 1, or alpha is equal to I minus 1 upon 2. The values of alpha found from these measurements and those found from the expression alpha is equal to lambda c upon lambda naught were found to be in fair agreement with each other for a number of electrolytes. This lent a great support to the Arrhenius theory. In general, for an electrolyte of the type AXBY, we have number of moles before dissociation 1 for AXBY and 0 for XA, Y positive, and YB, X negative. Number of moles after dissociation 1 minus alpha for AXBY and X alpha for XA, Y positive, and Y alpha for YB, X negative. Therefore, total number of moles after dissociation is equal to 1 minus alpha plus X alpha plus Y alpha is equal to 1 minus alpha plus alpha into X plus Y is equal to 1 minus alpha plus alpha n is equal to 1 plus alpha into n minus 1, where n is equal to X plus Y represents the total number of ions produced from the dissociation of one molecule of AXBY. Thus, as before, I is equal to 1 plus alpha into n minus 1 upon 1, which gives alpha is equal to 1 I minus 1 upon n minus 1. Fifth, ionic nature of reaction. As stated in postulate 7 of the Arrhenius theory, the properties of an electrolyte are the properties of its ions. Thus, the reaction between NaCl solution and AgNO3 solution forming a precipitate of AgCl may be explained as follows. NaCl is aqueous solution ionizes as NaCl gives out Na positive plus Cl negative. AgNO3 also ionizes in the aqueous solution as Ag positive and NO3 negative. When the above two solutions are mixed, we have Na positive plus Cl negative plus Ag positive plus NO3 negative gives out AgCl plus Na positive plus NO3 negative. The reaction between any two ionic compounds in aqueous solution takes place in a similar manner. Sixth, heat of neutralization. The heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is neutralized by the base or 1 gram equivalent of the base is neutralized by the acid. The heat of neutralization of a strong acid with a strong base is always the same. We have 13.7 kilocalorie or 57.3 kilojoule. This is explained by the Arrhenius theory as follows. Suppose the strong acid is HCl and strong base is NaOH. As both are completely dissociated in the aqueous solution, the reaction between them may be written as Na positive plus OH negative plus H positive plus Cl negative gives out NaCl plus H2O. Because the salt formed NaCl is also completely dissociated. Cancelling out the common ions on both sides, the above reaction reduces to H positive plus OH negative gives out H2O. Thus, neutralization may be defined simply as the process in which H positive ions given by acid combine with the OH negative ions given by the base to form unionized water molecule. As 1 gram equivalent of any strong acid in aqueous solution gives the same number of H positive ions and 1 gram equivalent of any strong base gives the same number of OH negative ions, the neutralization involves the combination between the same number of H positive ions and OH negative ions. Hence, the heat of neutralization of a strong acid with the strong base is always the same. If either the acid or the base or both are weak, the heat of neutralization is less than 13.7 kilocalorie or 57.3 kilojoule. The reason for the lower value is that a weak acid or a weak base dissociate to a small extent and some heat is used up to bring about its dissociation. For example, if the weak acid is acetic acid CH3COOH and the base is NaOH, they dissociate in the aqueous solution as follows. CH3COOH dissociate into CH3COO negative plus H positive and NaOH gives Na positive plus OH negative. As H positive ions are removed by combination with OH negative ions, the equilibrium shifts towards right, that is more of acetic acid dissociates. For acetic acid, the heat of neutralization is 0.5 kilocalorie per mole or 2.1 kilojoule per mole. Hence, the net heat evolved is 13.7 minus 0.5, that is 13.2 kilocalorie or 55.2 kilojoule. Similarly, the heat of dissociation of NH4OH is 1.4 kilocalorie per mole or 5.8 kilojoule per mole, so that the heat of neutralization of NH4OH with HCl is 13.7 minus 1.4 is equal to 12.3 kilocalorie or 51.5 kilojoule. Seventh, salt hydrolysis. It is defined as the process in which the salt reacts with the water to give back the acid and base. Salt plus water gives out acid plus base. Depending upon the relative strengths of the acid and the base produced, the resulting solution is acidic, basic or neutral. These observations are also explained on the basis of Arrhenius theory. Next heading 2.8, Ostwald's dilution law. According to Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and the undissociated molecules. For example, for a binary electrolyte AB, we have AB gives out A positive plus B negative. Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to this ionic equilibrium. As a result, he obtained an important relationship known as Ostwald's dilution law. Suppose the initial concentration of binary electrolyte AB in the solution is C moles per liter and alpha is the degree of dissociation, then we will have initial concentration C moles per liter for AB and 0 for A positive and B negative. Concentration at equilibrium C minus C alpha for AB and C alpha for A positive and B positive, which is equal to C into 1 minus alpha. Applied the law of chemical equilibrium, we get K is equal to A positive into B negative upon AB. That is equal to C alpha into C alpha upon C into 1 minus alpha. K is equal to C alpha square upon 1 minus alpha. The equilibrium constant K for the equilibrium AB gives out A positive plus B negative is called the dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd or Ki like any other equilibrium constant. Kd is constant only at room temperature. The units of Kd will be same as those of the concentration C. If the degree of dissociation alpha is very small, as it usually the case of for weak electrolytes at ordinary concentrations, alpha can be neglected in comparison to 1 in the denominator of expression I. Then the approximate formula becomes Kd is equal to C alpha square or alpha square is equal to Kd upon C. Approx formula alpha is equal to root Kd upon C. Equation 1 and 2 are the two expressions of Ostwald's dilution law. Expression 2 can be expressed in words as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial molar concentration. Further, as C is the concentration in moles per liter, therefore the volume V of the solution containing 1 mole of the electrolyte will be 1 upon C liters, putting 1 upon C is equal to V. The expression first and second can also be written as Kd is equal to alpha square upon 1 minus alpha into V and alpha is equal to root Kd upon V, where V is the volume of the solution in liters containing 1 mole of the solute. Thus, Ostwald's dilution law may also be defined as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is directly proportional to the square root of volume in liters containing 1 mole of the electrolyte. Validity of Ostwald's dilution law. To test the validity of Ostwald's dilution law, that is, to verify the law experimentally, the degree of dissociation alpha was determined from conductance measurements using the formula alpha is equal to lambda C upon lambda naught at different concentrations for a number of electrolytes. For each electrolyte, the data were fitted in equation 1 to see whether the value of Kd comes out to be constant or not. It was observed that first, the value of Kd comes out to be constant only for weak electrolytes, and that too when the concentration of the solution is not too high, that is for dilute solution only. Second, the value of Kd does not come out to be constant for strong electrolytes. Thus, it may be concluded that Ostwald's dilution law is valid only for weak electrolytes in dilute solutions. That is why it is called Ostwald's dilution law, and it does not hold good for strong electrolytes. As an example, the results of a weak electrolyte, namely CH3COOH, and those of a strong electrolyte, namely KCl, are given in table 2.2. Importance of Ostwald's dilution law. Ostwald's dilution law is applicable to weak electrolytes only. As such, it is very useful in the calculation of the dissociation constant Kd of the weak acids and weak bases by determining the degree of dissociation alpha from conductance measurements lambda C upon lambda naught at any concentration C, having determined the value of Kd, which is constant for a particular weak acid or weak base at a particular temperature. The degree of dissociation alpha of that weak acid or weak base can be calculated at any concentration C. Then there are some numerical problems on Ostwald's dilution law. Next, heading 2.9, limitations of Arrhenius theory. No doubt, Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolytes. A few of these objections are as follows. First, Arrhenius suggested that ionization of the electrolyte takes place when dissolved in water. However, X-ray studies have shown that many such electrolytes are already in the ionized state, example NaCl. Hence, the word ionization has been replaced by the word dissociation. Second, as an electrolyte can conduct electricity even in the molten state, it shows that dissociation of the electrolyte takes place even in the molten state. As such, the function of water could not be explained by the Arrhenius theory. In other words, it could not explain why the dissociation take place at all. Third, the most serious objection against Arrhenius theory was its utter failure when applied to strong electrolytes. Example A. Ostwald's dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolytes, that is, a constant value of the dissociation constant K is not obtained. B. The degree of dissociation alpha of strong electrolytes calculated from conductance measurements alpha is equal to lambda C upon lambda naught was found to be different from the calculated from colligative properties. The values were found to be nearly same only for univalent electrolytes. C. Strong electrolytes are almost completely dissociated even at moderate concentrations, that is alpha is equal to 1 or 1000 or 100% at all concentrations. Hence Arrhenius view that conductance increases with dilution because the dissociation increases does not make any sense. In case of strong electrolytes, the increase in conductance with dilution must be therefore due to some other factors called interionic effects discussed in the next section. The ratio lambda C upon lambda naught is therefore better than called apparent degree of dissociation or conductance ratio only. The failure of Ostwald's dilution law for strong electrolytes is evidently because of two reasons. Firstly, strong electrolytes are almost completely dissociated in the solution, therefore the question of equilibrium does not arise. Secondly, the calculation of alpha from lambda C upon lambda naught is faulty as mentioned above. Next heading 2.10, explanation of the anomalous behavior of strong electrolytes in interionic effects, Debye-Huckel theory. The increase of equivalent conductance with dilution in case of weak electrolytes can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increases because the dissociation of the weak electrolyte increases with dilution. However, in case of strong electrolyte, as they are almost completely dissociated even at moderate concentration, the increase in equivalent or molar conductance with dilution must be due to some other factors. The qualitative explanation put forward is as follows. The conductance of the solution of an electrolyte depends not only upon the number of ions but also upon their speed. In case of weak electrolytes, the increase in conductance with dilution is due to the increase in the dissociation of the electrolyte, that is due to the increase in the number of ions. The speeds of the ions in this case are not much affected by change in concentration because the number of ions produced is so small that the distance between them is quite large, so that there is no interference in the movement of an ion by the other ions. However, in case of strong electrolytes, the number of ions produced on dissociation is so large that the freedom of movement of an ion is hindered by the other ions present around it. When the solution is diluted, the ionic interference decreases and hence ionic speed increases, and so does the equivalent or molar conductance. The first successful attempt to explain the various variation of equivalent or molar conductance of strong electrolytes with dilution or concentration quantitatively was made by Debye and Huckel 1923. The fundamental idea underlying their work is that because of electrical attraction among the oppositively charged ions, each ion is surrounded by a large number of oppositively charged ions, which may be regarded as an ionic atmosphere of opposite charge, and this affects the speed of the ion in an electric field. The electrical attraction among oppositively charged ions which affect the speed of an ion in the electric field are called interionic effect. There are two such effects which are briefly described below. First, the relaxation effect or asymmetry effect, in which solution each ion is surrounded by an ionic atmosphere of oppositive charge so long as no electric field is applied. The ionic atmosphere remains symmetrical around the central ion. However, when a current is passed through the solution, the central ion moves towards the positively charged electrodes. It is moving out of the ionic atmosphere, it has to rebuild an ionic atmosphere of opposite charge around it, and the old ionic atmosphere dies out. However, neither the destruction of old ionic atmosphere nor the formation of new ionic atmosphere takes place instantaneously. Each of them takes some time called the time of relaxation. During this time, the old ionic atmosphere pulls the moving ion backward and hence retard its motion. Hence, the effect is called relaxation effect. Alternatively, it may be argued that as the central ion moves, the symmetry of the ionic atmosphere lost. More ions of the ionic atmosphere are left behind them are present on the front. The excess ions of the ionic atmosphere present behind the moving ion drag the ion backward and retard its motion. Thus, the effect arises because of asymmetry of ionic atmosphere of moving ion and hence is also called asymmetry effect. Second, electrophoretic effect. When EMF is applied, the central ion moves in one direction and the positively charged ionic atmosphere moves in the opposite direction. As this ionic atmosphere moves, the solvent molecules associated with it also move along with it. Thus, the flow of ionic atmosphere and that of the solvent molecules attached to it takes place in a direction opposite to that of the movement of the central ion. In other words, the central ion is moving against the steam, hence its motion is retarded. This effect is called electrophoric effect since it is similar to that of opposing the movement of colloidal particles is an electric field. Alternatively, it may be suggested that in a concentrated solution, the ions are so close that the positively charged ions may combine to form ion pairs. Thus, in a concentrated solution, ion pair exist, that is, by dissociation is not completely, though ionization is complete. Besides the above two effects, the third retarding force is the normal frictional resistance offered by the medium, which depends on the viscosity of the medium, its dielectric constant, etc. Based upon the above ideas, Debye and Huckel 1923 derived a mathematical expression for the variation of molar conductance and concentration. This equation was further improved by Onsager 1926-27 and now equation is known as Debye-Huckel-Onsager equation or simply Onsager equation for a univalent electrolyte. It is written in the form of lambda mc is equal to lambda m naught minus 82.4 upon dt power 1 upon 2 eta plus 8.20 into 10 raised to power 5 upon dt power 3 upon 2 into lambda m naught into root c, where lambda mc is equal to molar conductance at concentration C, lambda m naught is equal to molar conductance at infinite dilution. D is equal to dielectric constant of the medium, eta is equal to coefficient of viscosity of the medium, T is equal to temperature of the solution in degrees absolute, C is equal to concentration of the solution in moles per liter. As D and eta are constant for a particular solvent, therefore at constant temperature the above equation can be written as in the form lambda mc is equal to lambda m naught minus a plus b lambda m naught into root c, where A and B are constant for a particular solvent at a particular temperature. Verification of the Onsager equation. Two tests can be readily performed to verify the Onsager equation. These are: first, the plot of lambda mc versus root c should be linear. Second, the slope of the line should be equal to a plus b lambda m naught calculated by substituting the values of various constants directly. The plots of lambda mc versus root c for some common univalent electrolytes dissolved in water at 25 degrees Celsius are given in figure 2.8. The lines represent theoretical slopes whereas small circles represent the experimentally observed points. Thus, the agreement is very fair. In case of certain salts like NaCl, KCl, it is observed that the agreement is excellent at low concentration, but at appreciable concentration the measured conductance are somewhat higher than those calculated from Onsager equation. It is probably because there may be some other retarding forces which have been neglected. Thus, the anomaly of strong electrolytes is not yet fully resolved. From equation second, it may be seen that an infinite dilution, that is when C is nearly equal to 0, lambda mc becomes equal to lambda m naught as expected. Significance of Debye-Huckel theory. The significance of Debye-Huckel theory obviously lies in the fact that it is able to explain why the molar conductance of a strong electrolyte at any concentration is less than the limiting value of lambda m naught at infinite dilution in spite of the complete ionization of the strong electrolyte. Next heading 2.11 Migration of ions and transport number. Heading 2.11.1 Migration of ions. When electricity is passed through the solution of an electrolyte, the ions present in solution are liberated at the electrodes, that is, electrolysis occurs. This movement of ions towards the oppositively charged electrodes is called migration of ions. That ions actually exist independently and move with the passage of current of solution towards the positively charged electrodes can be seen experimentally as follows. Take a U-tube, fill its lower portion by CuCr2O7 jelly obtained by a mixing a 5% solution of agar-agar and a mixture of CuSO4 and K2Cr2O7 and allow it to set. The jelly is green in color. To mark the position of jelly, some charcoal is scattered over the green jelly. Over charcoal in both the limbs is added KNO3 solution is agar-agar, that is KNO3 jelly, and then aqueous solution of KNO3. When current is passed, blue-colored Cu2 positive ions are seen moving towards negative electrode and yellow-colored Cr2O7 2 negative ions are seen moving towards positive electrode. After some time, the two types of ions are seen moving with well-defined boundaries. The experiment clearly shows the migration of ions. Next heading 2.11.2 Migration velocity of ions and change in concentration. Hittov's theoretical device. According to Faraday's second law of electrolysis, when the same quantity of electricity is passed through solution of different electrolytes, the ions are always liberated in equivalent amounts. This, however, does not necessarily mean that the ions move with the same speed. It may be illustrated as follows. Consider a cell containing the solution and provided with the anode A and a cathode C. Let the solution lying between the electrodes A and C divided into three compartments, the anodic, the middle, and the cathodic, with the help of imaginary porous partitions A and C shown by dotted lines. Before electrolysis, suppose there are 13 pairs of ions, positive sign indicating the cation and the negative sign the anion, 4 being present in each of the anodic and the cathodic compartment and 5 in the middle as shown in position 1. Now the following different cases may be considered. Case 1. When only anions negative move. Let two anions leave cathodic compartment and enter anodic compartment. We got the position second. Although the cations have not moved, still we see that the number of ions liberated in the same at both the electrodes, but we see that concentration in anodic chamber has not altered while that in cathodic chamber has fallen by 2 molecules. Similarly, we can show that if cations are capable of movement of 2 of them enter cathodic compartment from anodic compartment, then there will be fall in concentration of 2 molecules in the anodic chamber. Thus, we see that velocity of an ion is proportional to the fall of concentration of chamber from where it leaves. Case second, when cations and anions move at the same rate. Let us assume that 2 cations move from anodic compartment to the cathodic compartment and 2 anions move from cathodic compartment to the anodic compartment when get position third. In this case, there is fall in concentration of second 2 molecules in each compartment, but we find that the number of ions liberated at both the electrodes is the same, that is 4. Case third, when cations move at double the speed of the anions. Suppose that 2 cations and anodic compartment leave and enter the cathodic compartment. Since the speed of anions is half the speed of cations, therefore only one anion enters the anodic compartment. The position is shown in fourth. We also observe that the fall in concentration in anodic and cathodic compartment are second and 2 and 1 molecules respectively. The number of ions discharged in again the same via 3 in each Conclusion. From the above illustration, we draw the following conclusion. First, fall in concentration around any electrode is directly proportional to the speed of ions moving away from it. It means fall in concentration around cathode is proportional to speed of anion, and fall in concentration around anode is proportional to speed of the cation. that is fall in concentration around anode upon fall in concentration around cathode, is equal to speed of cation upon speed of anion. Second, irrespective of the speeds of the ions, the number of ions liberated on both the electrodes is equal. Instead of number of ions, we can speak of the number of gram equivalents of the ions deposited on the electrodes depending upon the number of farads of electricity passed. Case fourth, when the electrodes are attackable. The above relationship has been derived on the assumption that the ions do not react with the electrodes, but in a silver voltmeter containing AgNO3 solution and having silver electrodes with NO3 negative ion that reaches the anodic compartment reacts with Ag of the electrode forming AgNO3, and instead of decrease there is an increase of concentration in the anodic compartment in a silver voltmeter. The above three cases are shown again in figure 2.11. It is seen that inversely case, that is always as increase in concentration in the anodic compartment. This increase in concentration takes place even when Ag positive ion migrate from anodic compartment to the cathodic compartment. Cases third and fourth. In order to find the increase in concentration that would have taken if so Ag positive ions had migrated from the anodic compartment to the cathodic compartment, a silver or a copper voltmeter, also called colorimeter, is placed in series. Suppose the number of gram equivalents of Ag or Cu deposited in this voltmeter is X. Obviously, X gram equivalent would have been the increase in the concentration of anodic compartment if no Ag positive ions had migrated from the compartment. However, the actual increase is less due to migration of Ag positive ions. Suppose the actual increase in the concentration of Ag in the anodic compartment is Y gram equivalent, hence fall in concentration in the anodic compartment due to migration of Ag positive ions is equal to X minus Y gram equivalent. Further, from figure 2.11, it may be seen that fall in concentration around cathode is equal to increase in concentration around anode is equal to Y gram equivalent. Thus, the speed ratio in this case will be given by speed of Ag positive ions upon speed of NO3 negative ion is equal to X minus Y upon Y. Next heading 2.11.3, transport number. As seen in section 2.11.1 and 2.11.2, when an electric current is passed, the ions migrate towards the electrodes. Thus, the electric current is carried by ions. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called the transport number or transference number or Hittorf's number. Greater the speed of the ion, greater the amount of current it will carry with it, and hence greater will be its transport number. Let UA and UC be the speeds of an ion and cation respectively. Then current carried by an ion is directly proportional to UA is equal to KUA. Current carried by cation is proportional to UC is equal to KUC. Since current is carried only by ions, therefore total current carried is equal to current carried by an ion plus current carried by cation is equal to KUA plus KUC is equal to K into UA plus UC. Therefore, transport number of an ion Na is equal to KUA upon K into UA plus UC, or Na is equal to UA upon UA plus. Similarly, transport number of the cation will be Nc is equal to UC upon UA plus UC. Two important relations. First, Na plus Nc is equal to UA upon UA plus UC upon UA plus UC is equal to UA plus UC upon UA plus UC is equal to 1, or Na plus Nc is equal to 1. That is, sum of transport numbers of an ion and cation of an electrolyte is always unity. Thus, no current is lost in any other fraction and the whole of the current is carried by the ions. Second, Na is equal to UA upon UA plus UC is equal to 1 upon 1 plus UC upon UA is equal to 1 upon 1 plus R, where R is equal to UC upon UA is equal to speed ratio of the cation to the anion. Similarly, UC is equal to UC upon UA plus UC is equal to UC upon UA upon 1 plus UC upon UA, or NC is equal to R upon 1 plus R. Thus, Na is equal to UA upon UA plus UC is equal to 1 upon 1 plus R. Nc is equal to UC upon UA plus UC is equal to R upon 1 plus R. Next heading 2.12, determination of Transport numbers. There are a number of methods for the determination of transport numbers, that is first Hitchcock's method, second Lorentz moving boundary method, and third EMF method. Out of these, the first two methods are described below. First, Hitchcock's method. Principle. The method is based upon the principle that the fall in concentration around an electrode is proportional to the speed of the ion moving away from it. That is, fall in concentration around cathode upon fall in concentration around anode is equal to speed of anion upon speed of cation is equal to UA upon UC. Adding 1 to both sides, we get 1 plus fall in concentration around cathode upon fall in concentration around anode is equal to UA upon UC plus 1, or fall in concentration around anode plus fall around cathode is upon fall in concentration around anode is equal to UA plus UC upon UC, or total fall in concentration around both the electrodes upon fall in concentration around anode is equal to UA plus UC upon UC, or fall in concentration around anode upon total fall in concentration around both the electrodes is equal to UC upon UA plus UC is equal to NC. If the concentration are expressed in terms of gram equivalent, the above expression may be written as Nc is equal to number of gram equivalent lost from the anodic compartment upon number of gram equivalent lost from both the compartment. Referring to figure 2.11, it may be seen that number of gram equivalent lost from both the compartment is equal to the number of gram equivalent discharged on each electrode. This in turn can be found by replacing a silver or a copper voltmeter in series, as according to Faraday's second law, when the same quantity of electricity flows through the silver or copper voltmeter, the same number of gram equivalent of Ag or Cu will be deposited. Thus, the above formula reduces to Nc is equal to number of gram equivalent lost from anodic compartment upon number of gram equivalent deposited in the voltmeter. Thus, the determination of the transport number of the cation Nc involves the determination of the number of gram equivalent lost from anodic compartment and the number of gram equivalent of Ag or Cu deposited in the voltmeter placed in series with the apparatus. However, it is important to note that the above result is applicable only when the electrodes are not attackable by the ions. If the electrodes are attackable, the result is calculated in a different manner, as discussed in the calculation at the end of this section. To determine the transport number of the anion Na, there is no need to find the loss in concentration of the cathodic compartment, because Na can be calculated directly from the equation Na is equal to 1 minus Nc. Apparatus. Evidently, the apparatus should be such that, first, it should consist of three compartments, namely the anodic, the cathodic, and the central compartment. Second, the solution of these three compartments should not mix with each other on electrolysis. And third, it should be possible to take out the solution of any compartment without disturbing the solution of other compartment. The above requirement and met in the apparatus shown in figure 2.12, it consists of J tube joined on its two sides to two vertical bubbled glass tubes. All the three, that is the U tube and two vertical tubes, have got the stopcocks at their bottom. The U tube is also provided with two stopcocks, one on either side at the top, so as to cut off the various compartments from each other when required. In the two vertical tubes are placed the anode and the cathode separately. There are platinum, especially anode, if it is desired that these should not be attacked by the ions. Alternatively, the anode and the cathode of silver or copper are taken, depending upon whether transport number of Ag positive ions or Cu2 positive ion is to be determined, in which case the anode is attacked by the anions. The apparatus is connected to a silver or copper voltmeter, also called coulometer, in series with the apparatus, together with a battery, a rheostat, a key, and a milliammeter, as shown in figure 2.12. Procedure. First, the apparatus is filled with the solution of the electrolyte, the transport number of whose ions is to be determined. Second, a silver or copper voltmeter is placed in series with the apparatus and various connections made as shown in figure 2.12. Third, before electrolysis, the concentration of the electrolyte is found by titrating a non-weight of the solution against a suitable reagent, example against KSCN solution for AgNO3 solution and against hypo solution for CuSO4 solution after adding Ki into it, etc. Fourth, now a current of 0.01 to 0.02 ampere is passed for 2 to 3 hours. A low current is used so that the change in concentration around electrode is not too high, as otherwise the diffusion may take place. Fifth, after electrolysis, the solution from anode compartment is taken out, weighed and then titrated as before to know the amount of the electrolyte present. Sixth, the weight of silver deposited in the silver voltmeter or that of copper in case of copper voltmeter is used is also determined. Seventh, the solution from the central compartment is also taken out and titrated to see that there is no change in concentration within the experimental errors. In case a change in concentration observed, the experiment is repeated. It is important to note that in these measurements, the weights of the solution are taken instead of volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volumes. Calculations. The methods of calculation may be illustrated by taking the example of AgNO3 as the electrolyte and using silver voltmeter in series. Case 1. When the electrodes are non-attacked, that is, the platinum electrodes are used. After electrolysis, suppose weight of the anodic solution taken out is equal to W1 gram. Weight of AgNO3 found to be present by titration is equal to W2 gram. Therefore, weight of water present is equal to W1 minus W2 gram. Thus, W1 minus W2 gram of the water contained W2 gram of AgNO3 after electrolysis. In terms of gram equivalent, W2 gram of AgNO3 is equal to W2 upon 170 gram equivalent of AgNO3 is equal to W2 upon 170 gram equivalent of Ag is equal to X gram equivalent, say. Hence, we can say that after electrolysis, W1 minus W2 gram of water contain X gram equivalent of Ag. Before electrolysis, suppose W3 gram of solution contain W4 gram of AgNO3. Therefore, weight of water present is equal to W3 minus W4 gram. Thus, W3 minus W4 of water contain W4 of AgNO3 before electrolysis. Therefore, W1 minus W2 gram of water will contain W4 upon W3 minus W4 into W1 minus W2 gram of AgNO3 is equal to Y gram equivalent C. This is same weight of water as taken after electrolysis. When the electrodes are not attacked, X is less than Y. Therefore, fall in concentration of the anodic compartment is equal to Y minus X gram equivalent of Ag. Suppose the weight of silver deposited in the silver voltmeter is equal to W gram is equal to W upon 108 gram equivalent of Ag is equal to Z gram equivalent. Therefore, transport number of Ag positive ion Nag positive is equal to fall in concentration around anode in gram equivalent upon amount of Ag deposited in voltmeter in gram equivalent is equal to Y minus X upon Z. Transport number of NO3 negative ions NO3 negative is equal to 1 minus Nag positive. Case second, when the electrodes are attacked, that is, when silver electrodes are used. In this case, as the NO3 ions reaching the anode attack the silver anode, there is increase in the concentration of Ag positive ions in the anodic solution instead of decrease, that is, in the solution. In this case, we will have X is greater than Y. Therefore, increase in concentration of the anodic solution is equal to X minus Y gram equivalent of Ag. This increase in the concentration takes place in spite of the migration of Ag positive ions from the anodic compartment to the cathodic compartment. If no Ag positive ions had migrated from the anode compartment, the increase in the concentration of Ag positive ions in the anodic compartment would have been higher and equal to Z gram equivalent of Ag, that is, the gram as the amount deposited in the silver voltmeter. Hence, fall in concentration in the anodic solution due to migration of Ag positive ions is equal to Z minus X minus Y gram equivalent of Ag. Therefore, transport number of Ag positive ions is equal to Z minus X minus Y upon Z. Transport number of NO3 negative ions is equal to 1 minus Nag positive as before. In case of copper voltmeter is used, the number of gram equivalent of copper deposited in the voltmeter is obtained by dividing the weight of copper deposited W gram by its equivalent mass. Second, moving boundary method. This method is based upon the fact that the transport numbers of the cation and anion are given by NC is equal to UC upon UC plus UA, and NA is equal to UA upon UC plus UA. Thus, by determining the speeds of the cation and the anion UC and UA, the transport numbers can be calculated. The apparatus used in shown in figure 2.13, it consists of a long tube mounted vertically and fitted with the platinum electrode on two sides as shown in figure 1.13. 2.13. The salt Ba under investigation is made into solution and then placed between the solutions of two other salts B-A and Ba-, one having a common cation and the other having common anion. For example, if Ba is KCl, B-A may be LiCl and Ba- may be CH3COOK. The three solutions are arranged in order of increasing density downwards to avoid mixing effects. The original boundaries are A and B. Even if the solution are colorless, the boundaries can be observed because of the differences in the refracting indices of the solution. In order that the boundaries may remain sharp throughout the experiment, B- and A- must have smaller velocities than B and A respectively, so that B- does not overtake B and A- does not overtake A. When the current is passed, the boundaries move to A- and B-. Thus, speed of the cation B positive is UC is directly proportional to length A-. Speed of the anion A negative UA is directly proportional to length B-B-. Hence, NC is equal to A-A- upon A-A- plus B-B- and NA is equal to B-B- upon A-A- plus B-B-. Next heading 2.13, factors on which transport number depends. It has been seen earlier that the transport number of an ion is directly proportional to the speed of the ion, which is in turn depends upon a number of factors. Example, first, nature of the ion. Normally, the smaller the size of the ion, greater is the speed and hence higher is its transport number. For example, the transport number of H positive ion in 0.1 N HCl is greater than that of Na positive ion in 0.1 N NaCl or K positive ion in 0.1 N KCl, etc. Second, nature of the other ion present. For example, the transport number of Cl negative ion NCl negative in HCl is different from that of Cl negative ion in NaCl. This may be explained as follows. NCl negative in HCl is equal to UCl upon UH plus UCl. NCl in NaCl is equal to UCl upon UNA plus UCl, where UH positive, UNA positive and UCl negative represent the speeds of H positive ion, Na positive and Cl negative ions respectively in their respective solutions. As Na positive ion is larger in size than H positive ion, UH positive is greater than UNA positive. As a result, the denominator of expression 1 is greater than that of expression 2. Hence, NaCl NCl negative in HCl is smaller than NCl negative in NaCl, as the numerator is same in both the cases. Third, hydration of the ions. The speed of an ion and hence its transport number is very much affected by the hydration of the ions. For example, lithium ions are smaller in size than sodium ions and hence may be expected to have higher transport number than Na positive ions, but the actual position in otherwise. This is because Li positive ions are more hydrated than Na positive ions. Similarly, Na positive ions have a smaller transport number than K positive ions. Fourth, concentration. The transport number of an ion changes with concentration, but the change in very small. However, in case the increase in concentration result into the formation of a complex ion, the transport number changes significantly. For example, the transport number of Cd2 positive ions in cadmium iodide solution falls from 0.444 in 0.005 m solution to 0.003 in 0.025 m solution. At still higher concentration, the transport number appears to be 0 or even negative. This is explained on the basis of the formation of the complex. CDI4 2 negative ions at higher concentration as follows. CDI2 gives out Cd2 positive aqueous plus 2I negative aqueous. CD2 positive aqueous plus 4I negative aqueous gives out CDI for 2 negative aqueous. In dilute solution, there are very few CDI for 2 negative ions, so that CD2 positive ions show their normal transport number. However, as the concentration is increased, more and more CDI for 2 negative ions are formed, which migrate to the anodic compartment. A stage comes when as many CDI for 2 negative ions migrate into the anodic compartment as the number of CD2 positive ions migrating away from it to the cathodic compartment. Thus, there is no change in the concentration of CD2 positive ions in the anodic compartment, and so that CD2 positive ion appear to have zero transport number. Fifth, temperature. As the temperature is increased, the ions tend to approach a transport number value of 0.5. That is, at this temperature, equal fraction of the current is carried by the cations and the anions. In case of ions having transport number less than 0.5 or ordinary temperature, the transport number increases with the increase of temperature. In case of ions having transport number greater than 0.5 at ordinary temperature, the transport number decreases with increase in temperature. When the transport number of the ions are approximately 0.5, as in KCl, the effect of temperature is very small. Sixth, interionic effect. How the speed of the ion is affected by the interionic effects has been discussed in section 2.10 under Debye-Huckel theory. Part 2, Kohlrausch law and applications of conductance measurements. Heading 2.14, Kohlrausch law of independent migration of ions. Kohlrausch studied the molar conductance at infinite dilution lambda m naught for a number of pairs of strong electrolytes, each pair having a common cation or anion. Then he calculated the differences of these lambda m naught values for each pair A. Few of these results are given in table 2.3. It is observed that the difference between lambda m naught values for each of sodium and potassium salt having a common anion was same irrespective of what this anion was. Similarly, the difference in the lambda m naught values for each pair of salts having the same different anions and a common cation was same irrespective of what the cation was. In fact, column 3 in the table 2.2 gives the lambda m naught value for K positive ion minus the lambda m naught value for Na positive ion. Similarly, the last column gives lambda m naught value for Br negative ion minus lambda m naught value for Cl negative ion. On the basis of the above observation, Kohlrausch concluded that each ion makes a definite contribution to the total molar conductance of an electrolyte and infinite dilution irrespective of the nature of the other ion of the electrolyte. This individual contribution of an ion towards the total molar conductance of the electrolyte is called the limiting molar ionic conductance. As a result of these studies, Kohlrausch in 1876 put forward a generalization known after him as Kohlrausch law. It states as under: the limiting molar conductance of an electrolyte at infinite dilution is the sum of the limiting molar ionic conductance of the cation and the anion, each multiplied with the number of ions present in the ion formula unit of the electrolyte. Mathematically, lambda m naught for AXBY is equal to x lambda A y positive naught plus y lambda B x negative naught, where lambda m naught is the limiting molar conductance of the electrolyte and lambda A naught and lambda B naught B negative are the limiting molar ionic conductance of the cation A y positive and the anion B x negative respectively. For example, lambda m naught for NaCl is equal to lambda Na positive naught plus lambda Cl negative naught. Lambda m naught for BaCl2 is equal to lambda Ba positive naught plus 2 lambda Cl negative naught. In terms of equivalent conductance, Kohlrausch law is defined as follows. The equivalent conductance of an electrolyte at infinite dilution is the sum of two values, one depending upon the cation and the other depending upon the anion. That is, lambda equivalent naught is equal to lambda C naught plus lambda A naught, where lambda C naught and lambda A naught are called the limiting equivalent ionic conductances, that is at infinite dilution, for the cation and the anion respectively. The above law is called the law of independent migration of ions because at infinite dilution the dissociation of the electrolyte is complete and there are no interionic effect, so that each ion migrates to the electrode independent of the nature of the other ion with which it is associated. It may be noted that molar conductance lambda m is related to the equivalent conductance lambda equivalent according to the expression lambda equivalent is equal to lambda m upon V positive Z positive, or lambda equivalent is equal to lambda m upon V negative Z negative, where V positive and V negative are the stoichiometric numbers of the cations and the anion respectively present in the formula unit of the electrolyte, and Z positive and Z negative are the charges on the cation and the anion respectively. As V positive, Z positive represent total charge on the cation, and V negative, Z negative represent total charge on the anion, and V positive, Z positive is equal to V negative, Z negative. Hence, we can write lambda equivalent naught is equal to lambda m naught upon total charge on the cation or anion, called N factor or valency factor. For example, for the salt sodium potassium oxalate, equivalent conductance is related to molar conductance, as lambda equivalent naught is equal to lambda m naught upon 2, as charge on the cation is equal to charge on the anion is equal to 2. Similarly, in the case of potash alum K2SO4 dot Al2SO4 whole thrice dot 24H2O, lambda equivalent naught is equal to lambda m naught upon 8, as total charge on the cation is equal to total charge on anion is equal to 8. Similarly, the ionic conductance lambda C naught m ohm inverse centimeter square equivalent inverse is equal to lambda C naught in ohm inverse centimeter square mole inverse upon charge on the cation. Lambda A naught in ohm inverse centimeter square equivalent inverse is equal to lambda A naught in ohm inverse centimeter square mole inverse upon charge on the charge on the anion. Next heading 2.15, ionic mobility and its relation with ionic conductance. Heading 2.15.1, ionic mobility. As the speed of the ion also depends upon the potential difference applied, hence a term ionic mobility has been introduced, which is defined as follows. The ionic mobility is the distance travelled by an ion in centimeter per second under a potential gradient of 1 volt per centimeter. That is, ionic mobility is equal to speed of the ion upon potential gradient applied. Next heading 2.15.2, relationship between ionic conductance and ionic mobility. As explained above, the term ionic conductance differs from the term ionic mobility. The two are found to be related according to the equation ionic mobility is equal to ionic conductance upon 96,500, in which ionic mobility and the ionic conductance are the limiting values, that is when the solution are very dilute, so that the electrolyte is completely dissociated. The above relationship has been derived as follows. Consider a solution contained in 1 centimeter cube and shade faces being electrodes as shown in figure 2.15. Then conductance of the solution is equal to specific conductance. By definition, if potential of 1 volt is applied between the electrodes, current flowing through the solution is equal to 1 upon R by Ohm's law, but 1 upon R is equal to conductance. Thus, under conditions stated above, current flowing through the solution is equal to specific conductance K of the solution. If the concentration of the solution considered above is C in gram equivalent per C, and if it is assumed that C is so small that the substance is completely ionized, then we know that equivalent conductance is equal to specific conductance upon C, or K is equal to C into lambda equivalent naught, but lambda equivalent naught is equal to lambda C naught plus lambda A naught by Kohlrausch law. K is equal to, therefore K is equal to C into lambda C naught plus lambda A naught, where lambda C naught and lambda A naught are the ionic conductance of the cation and the anion respectively at infinite dilution, but specific conductance K is equal to the current flowing through the solution as already explained above. Hence, current flowing through the solution is equal to C into lambda C naught plus lambda A naught. Now, if U C naught and U A naught represent the absolute velocity of the cation and the anion respectively, which are same as ionic mobilities because potential gradient is 1 volt per centimeter, it means that all the cation within a distance of UC naught centimeter from the cathode will move to it in 1 second. Similarly, all the anions with a distance of A naught centimeter from the anode will move to the anode in 1 second. As the solution contains C gram equivalent, therefore cation shifting to the anode in 1 second is equal to C mu C naught gram equivalent, and anion shifting to the anode in 1 second is equal to C mu A naught gram equivalent by Faraday's law. For every 1 gram equivalent of the ion discharged, 96,500 coulombs 1F if of electricity flows through the solution. Hence, for a discharge of C mu C naught and C mu A naught gram equivalent, current flowing through the solution is equal to 96,500 C mu C naught plus C mu A naught is equal to 96,500 C into mu C naught plus mu A naught. From equation 1 and 2, 96,500 C into mu C naught plus mu A naught is equal to C into lambda C naught plus lambda E naught, or or mu C naught plus mu A naught is equal to lambda C naught upon 96,500 plus lambda A naught upon 96,500. This leads to the result mu C naught is equal to lambda C naught upon 96,500 and mu A naught is equal to lambda A naught upon 96,500. Next heading, calculation of molar ionic conductance. The ionic conductance can be calculated from transport number measurements using the expression that may be derived as follows. As already stated above, that is, lambda C naught is proportional to mu C naught, or lambda C naught is equal to K mu C naught, and hence lambda A naught is proportional to mu A naught, or lambda A naught is equal to K mu A naught, where lambda C naught and lambda A naught are the ionic conductances and mu C naught and mu A naught are the ionic mobilities of the cation and the anion respectively, and K is the constant of proportionality. Dividing equation 3rd by equation 4th, we get lambda C naught upon lambda A naught is equal to mu C naught upon mu A naught. Adding 1 to the both side, we get lambda C naught plus lambda A naught upon lambda A naught is equal to mu C naught plus mu A naught upon mu A naught. Taking reciprocal of the both sides, we get lambda A naught upon lambda C naught plus lambda A naught is equal to U A naught upon mu A naught plus U A naught. But U A naught upon U C naught plus U A naught is equal to Na, transport number of the anion, and lambda C naught plus lambda A naught is equal to lambda equivalent conductance at infinite dilution by Kohlraasch law. Lambda A naught, therefore lambda A naught upon lambda equivalent is equal to Na, or lambda A naught is equal to Na into lambda equivalent naught. Similarly, lambda C naught is equal to Nc into lambda equivalent naught. Thus, limiting ionic conductance of an ion is equal to transport number of that ion into limiting equivalent conductance of a strong electrolyte containing that ion. This gives ionic conductance in ohm inverse centimeter square gram equivalent inverse. Similarly, molar ionic conductance in ohm inverse centimeter inverse mole inverse can be calculated using the expression limiting molar ionic conductance is equal to transport number of that ion into limiting molar conductance of a strong electrolyte containing that ion. Limiting molar ionic conductance lambda m naught, some common ions in water at 25 degrees Celsius 298 Kelvin in Simon centimeter square mole inverse are given in table 2.4. Next heading, 2.17, effect of viscosity of solvent on ionic conductance, Walden's rule. It is obvious that greater is the viscosity of the solvent used to make the solution, less is the mobility of the ion, and hence less is the ionic conductance. It is found that lambda naught eta naught is equal to constant and lambda naught eta naught is equal to constant. Hence, lambda positive naught plus lambda negative naught into eta naught is equal to constant, that is, lambda equivalent naught into eta naught is equal to constant. Thus, the product of the limiting ionic conductance of an ion and the coefficient of the viscosity of the medium is constant, or the product of the equivalent conductance of an electrolyte at infinite dilution and the coefficient of viscosity of the medium is constant. This is called Walden's rule. In case of ions, the above rule is found to hold good only if the ions are large in size, or for smaller ions if the solvent is other than water. Even in that case, the results are not very satisfactory. The reason for the failure in case of smaller ions is that they are solvated to different extent in their different solvents, and so their effective radii differ. Next heading, 2.18, effect of temperature and pressure on ionic conductance. Ionic conductance increases with increase of temperature. For all ions except H positive and OH negative ions, the increase is about 2% per degree, that is temperature coefficient is 0.02, while for H positive and OH negative the increase is about 14% and 16% respectively, that is temperature coefficient are 0.14 and 0.16 for all ions except H positive and OH negative, which follows some different conduction mechanism. The increase is due to decrease in viscosity with increase in temperature, which is about 2% per degree. Ionic conductance decreases with increase in pressure, which it again considered to be due to increase in viscosity with increase in pressure. Next heading 2.19, application of Kohlrausch law or application of conductance measurements. Heading 2.19.1, determination of equivalent or molar conductance at infinite dilution, lambda equivalent naught or lambda m naught for weak electrolytes. As already mentioned, the equivalent or molar conductance of a weak electrolyte at infinite dilution cannot be determined experimentally. Firstly, because the conductance of such a solution is low, and secondly, because of the dilution of such an electrolyte is not complete even at very high dilution. The equivalent or molar conductance of such an electrolyte at infinite dilution can be calculated using Kohlrausch law in any one of following two ways. First, consider the example of acetic acid CH3COOH as the weak electrolyte by Kohlrausch law. Lambda equivalent naught CH3COOH is equal to lambda naught CH3COO negative plus lambda naught H positive. This equation can be arrived at by knowing the equivalent conductance at infinite dilution for the strong electrolyte KCl, CH3COK and HCl, as by Kohlrausch law. Lambda equivalent naught KCl is equal to lambda K naught plus lambda Cl naught. Lambda equivalent naught for CH3COOK is equal to lambda CH3COO naught plus lambda K naught. Lambda equivalent naught for HCl is equal to lambda H naught plus lambda Cl naught. Hence we have lambda equivalent naught for CH3COOH is equal to lambda equivalent naught for CH3COOK plus lambda equivalent naught for HCl minus lambda equivalent naught for KCl. Second, considering the example of acetic acid, again we have by Kohlrausch law lambda equivalent naught CH3COOH is equal to lambda CH3COO naught plus lambda H naught. Each of the ionic conductance lambda CH3COO negative naught plus lambda H positive naught can be found from the measurements of transport number and equivalent conductance at infinite dilution of strong electrolyte containing that ion, that is lambda CH3COO naught is equal to N CH3COO in CH3COOK solution into lambda equivalent naught CH3COOK, and lambda H positive naught is equal to NH positive in HCl into lambda equivalent naught HCl. Next heading 2.20, conductometric titration. In addition to various applications discussed above, one of the most important application of conductance measurement is in the determination of endpoints of different types of titration. The basic principle of all these titration is that when one solution from the burette is added to another solution takes in the titration flask or a beaker, some ions of the later solution are replaced by those of the former, and hence the conductance changes. A few examples are illustrated below. First, titration of a strong acid with strong base. Suppose a solution of HCl is to be titrated against NaOH solution. For this purpose, the acid solution is taken in a beaker and the NaOH solution in the burette. The conductance of the acid solution is noted initially as well as after successive additions of smaller amount of NaOH solution. Evidently, conductance of the acid solution in the beginning is very high because it contains highly mobile H positive ions. As NaOH solution is added to the HCl solution, as H positive ions are replaced by the slow moving Na positive ions, and hence the conductance of the solution keeps on falling till the end point is reached. After the end point, further addition of NaOH solution introduces fast moving OH negative ions, and hence the conductance of the solution again begins to increase. Thus, if conductance values are plotted against the values of alkali added, a curve of type ABC is obtained as shown in figure 2.16. Obviously, the point of intersection corresponds to the endpoint. Second, titration of a weak acid with strong base. Suppose a weak acid like acetic acid is titrated against a strong base like NaOH. The conductance of the acid initially is very low because of low ionization of the acid. However, as NaOH solution is added more and more to the acid solution, the salt produced CH3COONA is highly ionized, and hence the conductance keeps on increasing along the line AB as shown in figure 2.17. When the solution of acetic acid has been neutralized further, the addition of NaOH solution causes the conductance to increase sharply along the line BC because the NaOH added introduces the fast moving OH negative ions. The equivalence point is again the intersection of the two lines AB and BC. Third, titration of a mixture of weak and strong acids with a strong base. When a mixture of weak and a strong acid like CH3COOH plus HCl is titrated against a strong base like NaOH, a curve of the type ABCD shown in figure 2.18 is obtained. The ionization of the weak acid remains suppressed in the presence of the strong acid because of the common ion effect. Hence, first the neutralization of only the strong acid takes place, and only after the neutralization of the weak acid starts. Thus, in the plot, the first point of intersection, that is point B, corresponds to the equivalence point for the complete neutralization of the strong acid, and the second point of intersection, that is the point C, corresponds to the equivalent point of the complete neutralization of the mixture. Fourth, titration of a strong acid with a weak base. Let us consider the titration of HCl against NH4OH solution. The conductance of HCl solution is initially high because of the presence of the fast moving H positive ion. As NH4OH solution is added, the fast moving H positive ions are replaced by the slower NH4 positive ions, and hence the conductance falls along the line AB. When the end points is passed, further addition of NH4OH does not cause much change in the conductance because NH4OH is weakly ionized substance. The line BC is thus almost horizontal. Fifth, precipitation titration. The most common example of this type of titration is that of AgNO3 solution against KCl solution. AgNO3 solution has some definite value of conductance in the beginning depending upon its concentration. As KCl solution is added to the AgNO3 solution, the following reaction takes place. Thus, the net result in the replacement of Ag positive ions of the AgNO3 solution by the K positive ions. Since both these ions have nearly equal ionic mobility, the conductance remains almost constant till the end point is reached. After the end point, further addition of KCl amount to the introduction of K positive ions and Cl negative ions, thus the conductance begins increase along the line BC as before. The point intersection corresponds to the equivalent point. Sixth, titration of a salt of a weak acid with a strong acid. For example, suppose hydrochloric acid is added to the sodium acetate solution. The following reaction takes place. Thus, as HCl is added, the net result is the replacement of CH3COO ions by Cl negative ions. As both these ions have nearly the same conductance, the conductance of the solution remains nearly constant till the end point is reached. After the point is crossed, the excess HCl added result in an increase of conductance. Thus, the shape of the plot is similar to that shown in figure 2.20. An important precaution in all the above titration is that the solution taken in the burette should be about 10 times stronger than taken in the titration flask, so that volume change of the later solution is negligible on the addition of the former solution. Advantages of conductometric titration. Conductometric titration have a number of advantages over ordinary titration involving the use of indicators. Example, first, this titration can be used for colored solution where ordinary indicators fail. Second, these can be used for the titration of even very dilute solution. Third, these can be used for the titration of mixtures of weak and strong acids. Fourth, as the end point is these titration is the intersection of two lines, no extra care, that is the drop-wise addition from the burette is needed near the end point. Next, heading 2.21, pH and pKa. Heading 2.21.1, definition of pH. We know that a solution may be neutral, acidic or alkaline. The ionic product of water Kw is equal to H3O positive into OH negative is equal to 1.0 into 10 raised to power minus 14 at 293 Kelvin. Always holds good. Thus, if H3O positive ion concentration of a solution is known. OH negative ion concentration is automatically fixed. Thus, to express the acidity or alkalinity of a solution, it is sufficient to express only the H3O positive ion concentration. Since the product of H3O positive and OH negative is always 1 into 10 raised to power minus 14, the concentration of H3O positive ion may be vary from 10 raised to power 0, that is 1 mole, to 10 raised to power 14 mole, to 10 raised to power 14 m. Thus, a solution may have H3O positive is equal to 2.5 into 10 raised to power minus 5 m, or which may be written as 0.00025 m. Obviously, such a method of expressing the H3O positive ion concentration is quite cumbersome. Sorensen in 1909 suggested a convenient method of expressing the H3O positive ion concentration in terms of pH. The symbol has been taken from the Danish word potenzide hydrogen ion, which means power of hydrogen ions. The following different definition of pH are used to express the H3O positive ion concentration. pH of a solution is defined as the magnitude of the negative power to which 10 must be raised to express the hydronium ion H3O positive concentration. Thus, if in a solution H3O positive is equal to 10 raised to power minus x, pH is equal to x. However, this definition can be used only where the H3O positive can be expressed as power of 10. In many cases, it may not be easy to do so. Example, a solution may have H3O positive is equal to 2.5 into 10 raised to power minus 5 gram. A more general definition may be arrived at from equation first as follows. Taking logarithm of both sides of equation 1, we get log H3O positive is equal to log 10 raised to power minus x is equal to minus x log 10 is equal to minus x. X is equal to minus log H3O positive, that is pH is equal to minus log H3O positive. This is the most common form used in numerical problems. Thus, pH may be defined as negative logarithm of hydronium ion concentration. Equation second may be rewritten as pH is equal to log H3O positive inverse, or pH is equal to log into 1 upon H3O positive. Hence, pH may also be defined as logarithm of the reciprocal of H3O positive ion concentration. Next, heading 2.21.2 pH scale. Theoretically, a solution may have any H3O positive ion concentration and hence may have any pH value. However, practically, the solution having H3O positive ion or OH negative ion concentration more than 10 raised to power 0 is equal to 1 m, and hence OH negative ion or H3O positive ion concentration less than 10 raised to power minus 14 m are not common. This is because such solutions are not easy to obtain, and moreover, as the concentration increases, the density of solution of the acid or the base decreases enormously. Hence, the pH range is taken as 0 to 14 for most of the practical purpose. The acidity or the alkalinity of a solution may be represented on the pH scale as follows. Next, heading 2.21.3 pOH, pKa and pKb. Just as we have pH is equal to minus log H positive, similarly we have pOH is equal to minus log OH negative, and pKa is equal to minus log Ka, and pKb is equal to minus log Kb, and pKw is equal to minus log Kw, where Ka and Kb represent ionization constant of the acid and the base respectively, and Kw is ionic product of water. Greater the value of ionization constant of the acid or the base, smaller is the value of pKa and pKb, and the stronger is the acid or base, and vice versa. Thus, larger the value of pKa and pKb, weaker is the acid or the base. For example, if two acids Ha1 and Ha2 have ionization constant Ka1 is equal to 10 raised to power minus 4 and Ka2 10 raised to power minus 5, then Ka1 is greater than Ka2 acid. Ha1 is stronger than Ha2 in terms of pKa values. pKa1 is equal to 4, pKa2 is equal to 5. Next, heading 2.21.4 relationship between pH and pOH. As stated above, just as pH is equal to minus log H positive, similarly pOH is equal to minus log OH negative. Since H3O positive OH negative is equal to Kw is equal to 10 raised to power minus 14 at 25 degrees Celsius, therefore log H3O positive plus log OH negative log Kw is equal to log 10 raised to power minus 14 is equal to minus 14, or minus log H3O positive minus log OH negative is equal to minus log Kw is equal to 14, or pH plus pOH is equal to pKw is equal to 14. Next heading 2.21.5 relationship between Ka, Kb or Kpa or Kpb value. Consider the weak acid HF. Its conjugate base is F negative. They dissociate as follows. HF gives out H positive plus F negative. Ka is equal to H positive into F negative upon HF. F negative plus H2O gives out OH negative plus HF. Kb is equal to OH negative into HF upon F negative. Multiplying equation 1 and 2, we get Ka into Kb is equal to H positive into OH negative is equal to Kw. That is Ka into Kb is equal to Kw. Therefore, log Ka plus log Kb is equal to log Kw, or minus log Ka minus log Kb is equal to minus log Kw is equal to minus log 10 raised to power minus 14. That is pKa plus pKb is equal to pKw is equal to 14. Next heading 2.21.6 limitations of pH scale. First, the pH values of the solution do not give the exact idea of their relative strength. For example, A solution of pH is equal to 1 has hydrogen ion concentration 100 times than that of solution of pH is equal to 3 and not 3 times. B a 4 into 10 raised to power minus 5 and HCl solution is twice concentrated as compared to 2 into 10 raised to power minus 5 and HCl solution, but the pH values of these solutions are 4.4 and 4.7 respectively, and not doubt. Second, pH is equal to 0 is obtained in 1N solution of a strong acid, and for concentration 2N, 3N, 10N, etc. the value can be negative 2. Similarly, for a concentrated solution of a strong base greater than 1 m, pH can be greater than 14. Third, a 10 raised to power minus 8 m solution of acid cannot have pH is equal to 8. The value will be closer to be less than 7. Similarly, 10 raised to power minus 8 m NaOH solution cannot have pH is equal to 6. The value will be closer to 7 but greater than 7. Next heading 2.21.7 effect of temperature on pH of neutral water. It may be remembered that Kw is equal to 10 raised to power minus 14 only at 298 Kelvin, and hence pH is equal to 7 for neutral water only at 298 K. As temperature is increased, dissociation of H2O molecules increase, producing large amount of H positive ion, that is H positive increases and becomes greater than 10 raised to power minus 7. Hence pH is less than 7. Higher the temperature, greater is the dissociation of H2O molecules. Higher the concentration of H positive ion, lesser is the pH than 7. Thus, pH of neutral water decreases more and more than 7 as temperature is increased. However, as many temperature H positive is equal to OH negative, water remains neutral. A few interesting results are given below. First, at 273 Kelvin, Kw is equal to 10 raised to power minus 14. Therefore, pH of neutral solution at this temperature is equal to 7.5 and pH scale is 0 to 15. Second, at 333 Kelvin, Kw is equal to 10 raised to power minus 13. pH of neutral solution is equal to 6.5 into, and pH range is 0 to 13. Third, at the temperature of human body, which is nearly 37 degrees Celsius, pH is neutral solution is equal to 6.8. Next heading, measurement of pH. Though accurate measurement of pH of a solution is done with the help of instrument called pH meter, approximate pH within the range of 0.5 can be determined with the help of pH paper, which show different colors when dipped in solution of different pH. Next heading 2.22 buffer solution. Definition. It is sometimes necessary that a solution of definite pH be prepared and stored. The preservation of such a solution is even more difficult than its preparation. If the solution comes in contact with air, it will absorb carbon dioxide and acidic and anhydride and becomes more acidic. If the solution is stored in glass bottle, the alkaline impurities present in the glass may dissolve into the solution and may alter its pH. A buffer solution is defined as the solution which resists any change in its pH value, even when small amount of acid or base are added to it. Next heading, types of buffer solution. There are two types of buffer solution. These are: first, solution of single substances. The solution of the salt of a weak acid and a weak base, example ammonium acetate, acts as a buffer. Second, solutions of mixtures. These are further of two types. A, acidic buffer. It is the solution of a mixture of a weak acid and a salt of this weak acid with a strong base. Example, CH3COOH plus CH3COONe or HCOOH plus HCOONe. B. Basic buffer. It is solution of a mixture of a weak base and a salt of this weak base with a strong acid. Example, NH4OH plus NH4Cl or NH4OH plus NH4NO3. Next heading, buffer action. The property of a buffer solution to resist any change in its pH value even when a small amount of the acid or the base are added to it, called buffer action. The buffer action of different types of buffers may be explained as follows. Buffer action of ammonium acetate solution. Ammonium acetate, like all other salts, is almost completely dissociated in the aqueous solution as follows. Thus, in the solution there is excess of CH3COO negative ions and NH4 positive ions. When a few drops of an acid, say HCl, are added to the above solution, the H3O positive ions given by the acid combine with the CH3COO negative ions to form weakly ionized molecules of CH3COOH. Thus, the H3O positive ion concentration of the solution does not change particularly, and hence the pH of the solution remains almost constant. Similarly, when a few drops of a base are added to the above solution, the OH negative ions given by the base combine with the NH4 positive ions to form weakly ionized molecule of NH4OH. Thus, the OH negative ion concentration and hence the H3O positive ion concentration or the pH of the solution remains almost. On the contrary, the solution of a substance like NaCl cannot act as a buffer because NaCl dissociate completely to give Na positive and Cl negative ions. These may combine with the base or the acid added to form NaOH or HCl, but these ionize completely to give back the OH negative ions or H3O positive ions. Thus, the H3O positive ion concentration of the solution changes and hence the pH of the solution changes. Buffer action of acidic buffer. For example, let us consider the buffer action of the acidic buffer containing CH3COOH and CH3COONa. Acetic acid dissociates to a small extent, whereas sodium acetate is almost completely dissociated in the aqueous solution as follows. By common ion effect, the ionization of CH3COOH is further suppressed. Thus, in the solution there are excess of acetate CH3COO negative ions and a small amount of H3O positive ions. When a few drops of an acid are added to the above mixture solution, the H3O positive ions given by the acid combine with the CH3COO negative ions to form weakly ionized molecules of CH3COOH. Thus, the H3O positive ion concentration and hence the pH of the solution remains almost constant. Similarly, when a few drops of a base are added, the OH negative ions given by the base combine with the H3O positive ions already present to form weakly ionized molecules of H2O. As the H3O positive ions are consumed, the equilibrium shifts towards right according Le-Chatelier's principle. Thus, more of CH3COOH dissociates to make up the loss of H3O positive ions. Hence, the H3O positive ion concentration or the pH of the solution does not change. Buffer action of basic buffer. The buffer action of a basic buffer, example NH4OH, NH4Cl, may be explained as follows. NH4OH dissociate to a small extent, whereas NH4Cl dissociate completely in the aqueous solution as follows. By common ion effect, the ionization of NH4OH is further suppressed. Thus, in the solution there are excess of NH4 positive ions and a small amount of OH negative ions. When a few drops of a base are added, the OH negative ions given by it immediately combine with NH4 positive ions to form the weakly ionized NH4OH. Thus, the H3O positive ion concentration of the pH of the solution remains unaffected. Similarly, when a small amount of an acid is added, the H3O positive ion given by it combine with the OH negative ion already produced by NH4OH in equilibrium. As the OH negative ions are consumed by the equilibrium shifts in the forward direction, thus more than NH4OH dissociate to produce more of OH negative ions, which makes up the loss of OH negative ions. Hence, the OH negative ion concentration and therefore the H3O positive ion concentration or the pH of the solution remains fairly constant. Retain in memory buffers are explained above are weak acid buffers and weak base buffers. However, solution as strong acid like HCl, HNO3, etc. of suitable concentration also acts as buffers with a low pH, and solutions of strong bases like NaOH, KOH of suitable concentration also act as buffer with a high pH. This is explained below. Strong acid buffer. A strong acid is completely ionized in the aqueous solution and hence H positive ion concentration is very high. The addition of a small amount of the acid or base has negligible effect on the pH of the solution. For example, addition of 1 cm cube of 0.1 m HNO3 to 100 cc of 0.01 m HCl changes its pH from 2 to 1.16, which is negligible change. Second, strong base buffers. A strong base is completely ionized in the aqueous solution and hence OH negative ion concentration is very high. The solution of a small amount of acid or base has negligible effect on the OH negative ion and concentration and hence the OH positive ion concentration of the pH. For example, addition of 1 cm cube of 0.1 m HCl to 100 cm cube of 0.01 NaOH solution changes its pH from 12 to 11.96, which is negligible change. Next heading, calculation of pH of a buffer mixture. A for acidic buffer mixture. Henderson-Hasselbalch equation. If the weak acid is Ha and its salt is Ba, then Ha plus H2O gives out H3O positive plus An negative. Ba gives out B positive plus A negative, which gives the equation pH is equal to pKa plus log salt upon acid, or pH is equal to pKa plus log conjugate base upon acid. B for basic buffer mixture, like BOH plus BA in a similar manner, POH plus is equal to pKb plus log salt upon base. Alternatively, the above equation can be expressed in different way. pH is equal to pKa plus log base upon salt, or pH is equal to pKa plus log base upon conjugate acid. Applying the formula, a buffer solution of required pH can be prepared knowing the value of Ka or Kb and suitably adjusting the ratio of salt upon acid or salt by base. A mixture of acetic acid and sodium acetate acts as a buffer solution around pH 4.75, and a mixture of NH4OH and NH4Cl acts as a buffer around pH 9.25. Next heading, buffer capacity or buffer index. It is defined as the number of moles of an acid or a base required to be added to 1 liter of the buffer solution so as to change its pH by 1 unit. Thus, buffer capacity is equal to number of moles of the acid or base added to 1 liter of the buffer upon change in pH is equal to D upon dpH. Buffer capacity of a buffer is maximum when the concentration of the weak acid and its salt or weak base and its salt are equal, that is when pH is equal to pKa or POH is equal to pKb. Next heading, 22.6 Importance of buffer solution. First, in biological process, the pH of our blood is maintained constant in spite of various acid and base producing reactions going on in our body. In the absence of its buffer nature, we could not eat a variety of foods and spices. The buffer action is due to the presence of carbonic acid H2CO3, bicarbonate ion HCO3 negative and carbon dioxide CO2 in the blood. Second, industrial process. The use of buffers is an important part of many industrial processes. Example, first in electroplating, second in the manufacture of leather, photographic materials and dyes, third in the preservation of food articles, third in analytical chemistry. Example, first in the removal of acid radicals such as phosphate, oxalate, borate, which interfere in the precipitation of radicals of group 3 of salt analysis. Second, In complexometric titration, example metal ions with EDTA, ethylene diamine tetraacetate. Third, to calibrate the pH meters. Fourth, in bacteriological research, culture media are generally buffered to maintain the pH required for the growth of the bacteria being studied.